Hello, everyone. This is the video lesson for the first day of exponential growth model. This is a model that you've seen before in an algebra class. Hopefully at this point you already have an idea of what the graph looks like, what the equation for exponential growth might look like. But today we look at it through the lens of calculus, and we look at the relationship between an exponential growth function and its own differential equation. Let's take a look at the next page here. Here we're starting with a differential equation. Notice it's variables y and t. Okay. The k here is a constant, but we've got dy dt equals constant k times y, which is notable because that tells us that the rate at which y is growing is based on how much of y there is to begin with. The rate of change of y with respect to t is proportional to the amount y. Okay, so what sort of function is going to grow faster when there is more stuff there? Well, you probably know where this is headed, but we can prove where we're going using our separation technique. Here is that first separation step, y stuff on the left, dt on the right. We'll leave the k over there as well. Antiderivatives, we see a plus c. We're seeing some of the same steps that we saw last week algebraically to eventually get y by itself, confirming that, yeah, y must equal a constant times e to the kt power. T being the variable, it's an exponent. So we've got our exponential model. Okay, so the goal here is to recognize these relationships in a word problem to potentially save you some time. For exponential models, when they do show up, you don't actually have to show the separation work unless a prompt specifically tells you to. You can skip straight from this highlighted differential equation right to the y equals. It'll save you some time. Sometimes you don't have the equation written in the equation form. You might read a certain sentence in the prompt. Rate of change of y with respect to t is proportional to the amount. And you can jump from there straight down to your y equals exponential growth. So we'll see an example of this on the next page. Oh, I lied, just kidding. Little more notes first. Okay, so this is just summarizing what we already know. If we see our particular equation, we automatically get the y equals for free. Here's what it means in words. Quick note about the k constant, whether it's positive or negative, is going to tell you if you have a growth model versus a decay model. Do we have an amount that's growing exponentially, or do we have an amount that's getting smaller, smaller, smaller over time? You'll also notice that I replaced the a on the previous page with y sub 0, or y naught, as it is sometimes called. This is commonly used just to remind us of the fact that that constant ends up representing the initial amount that you start with when t equals 0. Imagine plugging a t of 0 in here. You're going to have e to the 0, which turns into 1. You get amount equals y naught. So just keep that in mind as well. Okay, now you're ready for an example. Nozama online retailer has a promotion at their brick and mortar store, their physical store, offering a one-day special deal for customers who agree to pick up their order in store. The function z of t approximates the number of orders that still need to be picked up t days after the promotion. So presumably people make the orders online. Some people show up pretty soon to pick it up. Some people might not do that right away. Okay. First part here, okay, dz dt equals negative 1/2 z. Notice that this is a z, not a t, z being the dependent variable, as it were. Z is the amount function. So this right here is your only tangible clue that we have an exponential model. It wasn't mentioned in the prompt. Okay. Z of 0 is 300. They're giving us the initial amount. Find Z of t. Yeah, you could do separation. You could plug in a point somewhere in there. But the quicker approach, recognizing our exponential model, is to go right to this. Z of t equals initial times e to the negative 1/2 t. Real quick. From there, it's pretty easy to use. You're going to see a lot of algebra again in this chapter. Okay. How many orders are left over after 2 days? We're just plugging in a 2 for t. All right. Turns out to be about 110 orders. You could check the math on that yourself if you like. Part B, about how many days after the promotion is the number of orders still waiting for pickup down to 250. This value that they're giving us is not a number of days, it is the number of orders. So this goes in as the value of the Z on the left side. And now we are solving for T. Okay, so again, algebra, right? I'm dividing by 300 and immediately simplifying that fraction down. Okay, we need to pull negative 1/2 t out of an exponent, right? So we've got a base of e here. We're going to take the log on both sides. Log of 5/6. Log of e to the negative 1/2 t. We get the nice cancellation from the log function in the exponential. Things are starting to look simpler. Okay. You need a calculator to get anywhere meaningful here. This answer doesn't necessarily resonate with us. Someone tells you, I had to wait -2 times natural log of 5/6 days. That doesn't mean anything, right? So calculator tells us a little over 1/3 of a day. After how many days is the number of orders? About 1/2 its initial value. Initial value, again, being the 300. We want our amount to be half of that. Not a coincidence, we end up with a 1/2 on the left side after some manipulation. And then go ahead and try the same tricks as the previous problem. See if you agree with my answer, t equals 1.386 days. So that was actually a decay version of an exponential model. Example on the next page, we're going to see a true growth. Oh no, there's a rumor going around that Sally's crushing on Billy. So of course, we're going to analyze it mathematically. Y of t represents the number of students who heard the rumor, t hours after it started. And here's what we needed. A dy dt equals a constant times y. This here is the one and only clue that we have the exponential model. Okay, but they don't give us the same sort of information beyond that. We don't have an initial amount. We do know 2 ordered pairs. 5 hours in, 6 students have known the rumor. 10 hours in, 9 students. Okay, so maybe it's not growing super fast just yet. First task, find the value of the k constant. This was not given to us in the prompt. Now we do know we have an exponential model, so I'm writing out a template for our function y of t equals an initial amount still unknown to us, e to the kt. How can I get these values? We have ordered pairs to plug in. I can plug in the 10, 9. 10 becomes the t, 9 is the amount. This equation by itself, not super helpful because there are still 2 unknowns in there. But we have a second ordered pair to plug in. And as you know, if we have 2 equations, 2 unknowns, there's usually a way to figure out what's going on there. In your algebra classes, you were probably more likely to combine equations via addition and subtraction, but it's also possible to combine with division. I'm going to take top equation, or rather I'm going to take the 9 from the top equation, divide it by the 6 from the bottom equation. Okay, if 9 is equal to this thing over here, and 6 is equal to this thing over here, then 9 over 6 should be equal to the ratio, the division problem, using those same expressions. From there, you get cancellation of your initial amounts. Exponent properties help us clean up the rest of it. And now we're just a couple steps away. Log on both sides. Do a little bit of division. It's not pretty, but here is the K constant. Okay. From there, we're going to move across horizontally. Next question, we'll do this one. How many students knew the rumor at the moment it started? These must be the people that created the rumor. Okay. And really, it's asking us to find this initial amount. Well, now we know what the K constant is. We can, again, plug in either one of the given ordered pairs. Once we do that, it's just a matter of algebra to solve for the initial amount. Okay, these things, believe it or not, clean up not so bad for us. The 5 times the 0.2, for example, that stuff goes away. E to the natural log of 1.5, right? That just becomes 1.5. Works out nice for us. This initial amount is 4. And with that, we now have the pieces to put together the full equation y of t. We now know what k is. We know what the y naught is. So there's the next part of it. Looks kind of messy. Turns out there is actually a way to write a simpler form of this without e, without natural logs. We're going to move across the right side of the page and check it out. Here is our equation once again. Okay. What I'm doing in the next step is I'm just reorganizing some parts of this exponent. I put the t with the 0.2 because this multiplier in front of the log can come up onto the 1.5 as an exponent. I'm trying to get stuff out of the way so I can more easily see that we've got e to the natural log of something. We get cancellation of functions here again. We're left with just 1.5 to the 0.2t. And of course, there was a 4 there as well. So it's just a little simpler version of this thing. All right, what's next? Go back over to the left side. We don't need to spend too much time here. We've seen this type of problem already. How many students know the rumor after 30 hours? We're just plugging in a 30 for t. You're probably using a calculator to finish that off. Looks like you're up to about 46 students at that point know the rumor. And one more question over on the right side. After how many hours do we hit 100 students? 100 is now an amount. We're solving for t. As you can see, I've used the simpler version from just above. A little bit easier to work with. Okay, but you're plugging in, moving a 4 over. It's really all algebra. So, pause the video, take a long look at it if you need to, but works out to be about 39.694 hours. All right. There's really just one more thing to talk about today. And honestly, this next bit, I haven't seen it on an AP test. I certainly am not planning on putting it on our test, but I think it might show up in some Delta math. So just to be safe, we'll cover it. And I'm sure you've seen it before in some class. But the compounding of interest, often used on bank accounts or loans or things like that, uses these exponential models. Here is a version where interest is compounded at certain increments throughout a given time period. So if this is a yearly sort of deal, okay, well, a sub 0 is your initial starting amount, a of t being the amount at some time t. R is an annual interest rate, but K is the number of times per year that the interest is actually added. All right, so instead of E to the KT, we see 1 plus R over K to the KT. Okay, so if you see problems using this in delta math, just pay close attention. Is there a mention of a certain number of times that interest is compounded per overall time period? You're probably going to use this formula. A little bit more common, however, is the continuously compounding interest. Here we see the more conventional initial times e to the RT. Maybe you learned it before as P times e to the RT. I don't know. Okay, but of course, R is the interest rate. A sub 0 is the initial. Super quick example on the next page. It's really more of an answer for you to check if you like, but suppose we have $1,200 deposited into an account of some sort. 30 years later, it's worth quite a bit more. So we're kind of working backwards a bit here to figure out what must the interest rate have been. So I'm taking my amount that we end with, setting it equal to initial times e to the RT, but now we have a value of t to plug in, which allows us to use algebra and solve for R. You should try it on your own. How long did it take for the original amount to double? Okay, again, here's my original amount. We want to end up with exactly double that. What's nice here is the a sub 0 cancels out. Again, not a coincidence that you end up with 2 being the multiplier on our original amount equals e to the RT. Now we know R. We can solve t using logs. I did not show the work. You can try it on your own, but it should be about t equals 9.6 years. Okay, so nothing too crazy in this lesson. We'll see some more examples tomorrow. If you have any questions, feel free to email me. Let me know how you're doing. Thanks for watching.